And we have covered the basic traffic flow models, the parameters. Okay, and we have covered the shock waves. And the last thing which we did was talk about the gap, okay, which is the headway when you're looking at it, or the available headway in which you can enter from the opposing lane or the conflicting lane. Uh, this is a point where I ended the last lecture, which is whenever we talk about flow or density, we consider that they are uh, uniformly divided. So if the flow is 360 vehicles per hour, then it is divided into equal uh, value for 5 minutes interval. Okay, this is our assumption. This is what we are looking at. And similarly, if uh, I have 360 vehicles in 1 hour, then within these vehicles I have a 10-second gap. Okay, so and this remains constant throughout the hour, which is not the case. Okay, the gap or the headway or the flow does not remain constant from 1 minute to another minute or between one pair of vehicles to another pair of vehicles. So these simplistic values are called uniform arrival or deterministic arrival. When you are looking at single value for every item, that this is going to be this much, and it doesn't change. Okay, this is a fixed value and doesn't change. So this is called as uniform or deterministic arrival. The opposite of that is called stochastic arrival, which means that for every value, there's a probability. This value may or may not happen based upon this much chance. So a flow of 360 vehicles per hour is not the only value which I can have or I can expect in this hour. I have a chance of having 350 vehicles as well. I have a chance of 400 vehicles as well. So 360 has its own chance. Basically, in a stochastic approach, every value has its probability. Yes, some values will be so out that their probability will be zero. Their chance will be zero. Okay, but the value still exists. So for any in the stochastic approach, we are not looking at fixed values. We are looking at values and their chance or values and their probability. So when we are talking about calculating probability, a very important item is what is the distribution this probability will follow. There are many distributions which are well defined in statistics, in probabilistic sciences. We have normal distribution, chi-square distribution. We already use them in the traffic engineering course. For arrivals or for headways between the vehicles, we use another distribution which is called as Poisson distribution. Okay, so Poisson distribution has this shape. You can see it's slightly tilted towards the lower side. The peak is towards the lower side. Okay, and as it goes from this peak to towards the middle, as the peak goes from the lower side towards the middle, okay, it has a factor which is called as lambda. Okay, so the position of the peak in Poisson distribution depends upon lambda. Okay, so what is lambda? You can see the equation over here. Okay, this equation gives you the probability of having a value x if the distribution followed is Poisson distribution. And you can see x can be any value from 0 to infinity. So even infinity has a chance here, or you can calculate the chance for infinity here as well. And even 0 has a chance here. Okay, so this is the main approach of stochastic. This is the main idea of stochastic approach, that all values have some type of chance. Okay, so going back to the Poisson distribution, you can see here we have x. So x is the value for which I'm calculating the chance. And then we have mu and we have lambda. Sorry, we have mu only, sorry. We have mu only. So mu is the average number of vehicles which are arriving in time t. Okay, average. So there is a value for which I'm looking for the chance, and there is an average value. The average value is mu. Okay, so x can change, but the average, as you know, will not change. Okay, so what is or how we can calculate mu? Mu can be calculated using lambda. Okay, so going back to the lambda which I was showing here. Okay, so uh, lambda is basically v upon t. Okay, where v is the volume, total number of vehicles arriving in time t. Okay, now time t is your observation time. Okay, so there's a small time and there's a capital time. Okay, they can be different or they can be same. If your observation time is exactly equal to the time for which you are calculating the chance, then they are equal. So I took the volume for 1 hour and I'm calculating the probability of vehicles for 1 hour as well. The small t and capital T become same. Okay, otherwise they are different. Okay, now what is the relationship between lambda and mu? Remember, I need mu here. Okay, so lambda is v upon t, and where t is the total time, and mu is lambda into small t. Okay, lambda into small t. Okay, you will see some examples. For example, let us say this example. So I have 360 vehicles in 1 hour. Okay, so this will be my lambda, where volume is 360 and capital T is 1 hour. Okay, and I want the probability of vehicles to for arrival in 5 minutes. So small t is 5 minutes. Okay, the volume which I have is for 1 hour. So capital T is 1 hour. But I am looking at 5 hours, 5 minutes now. Okay, so small t becomes 5 minutes. So mu will be 360 into 5, but obviously this is in hours per hour and this is in minutes. So you need to convert one of them. Either convert minutes to hours or either convert hour to minutes. Okay, so you have to take care of the units here. So then lambda will be 360 per hour and then t will be 5 minutes converted to hour. Okay, so that will give you mu. So if you replace the value of mu in this equation with lambda into t, the equation will be this one. Okay, okay, so the equation will be this one. So we have lambda t x and that's it. Okay, and this is e to the power. So lambda is your vehicles in that full time. E is the time for which you are calculating the x, and x is the value for which you are calculating the chance. Okay. So for example, uh, the headway between two vehicles is, let's say, 2 seconds. Okay. The headway between two vehicles is 2 seconds. Okay. Now if I take small t as 1 second, okay, so between two vehicles I have a headway of 2 seconds. If I take small t as 1 second, okay, so what is a chance that a vehicle will arrive in 1 second if the headway between the two vehicles is 2 seconds? Is there a chance that a vehicle can arrive in 1 second? Tell me, yes or no? If between two vehicles I have a headway of 2 seconds, is there a chance that a vehicle can arrive in 1 second? Or sorry, let me rephrase the question. Let's say the chance. If the headway between two vehicles is 2 seconds, okay, then how many vehicles you can expect in 1 second? The headway is 2 seconds. So headway means time interval between two vehicles. Okay, if the time interval between two vehicles is 2 seconds, so should we expect any vehicle to arrive in 1 second? Yes or no?
No.
No. Yeah, we cannot. Okay, because the interval is 2 seconds. Okay, so less than 2 seconds, we are not expecting any vehicle there. Okay, because the next vehicle will at least take 2 seconds to come. Okay, So this is what they are saying here. If you put the t less than headway, then you have zero vehicles. X will become zero. Okay, P for zero. Okay, so P for zero means the time you have taken is uh, less than the headway. Okay, so the vehicles which can arrive becomes zero. Okay, so if you put x equals to zero, so 0 factorial becomes 1. Lambda t to the power 0 becomes 1. So the only thing we have is this one. Okay, so all x are gone here. You are only playing with lambda and t. Okay, so if you are looking for zero vehicles to arrive, your equation becomes simplified. Okay, if you are looking for the chance of zero vehicles arrived, you can use this simplified equation. Zero vehicles arrive, what does it mean? That you put this t so small that even it is even smaller than the headway of the vehicles. Okay, the time interval between the vehicles. So it becomes zero. Okay, number of vehicles become zero. Okay, so uh, where small t should be any value at least zero. So t cannot be negative, time cannot be negative. So this is what they are showing here. Okay, so if the probability of zero vehicles or the probability of time less than headway, less than or equal to headway, is this one, then the probability of time more than headway will be 1 minus this one. Okay, this is what we call as complementary probability. You may have heard about it, what we call as complementary probability. What is complementary probability? If chance of something, let's say A, is because we already use X, is let's say P1, then chance of uh, not A will be equal to 1 minus P1. Okay, this is what we call as complementary probability. If chance of having something is a value, then chance of not having it is 1 minus that value. Okay, this is what we call as complementary probability. So this is the item, this is the rule they are using here. If chance of having t less than headway is this much, then chance of t more than headway will be this much. Okay, 1 minus this. Okay, and if you add both of them, then it should always be equal to 1. Okay, this is pretty straightforward. Okay, the summation of chances is always equal to 100%. Either you have 100% chance or less than that, right? So if I add both the parts, you get 1 or 100%. Do you have any questions at this time? I just give you like 5 seconds to think. Do you have any questions in this whole discussion? Okay, very well. So what we said traffic flow is not a fixed or deterministic value. It has a chance of every value. Okay, and that chance can be represented with a Poisson distribution. According to Poisson distribution, the chance or the probability can be calculated using this. Okay, then we define the mu term here in terms of lambda and t. And then we said if you are looking for the chance of zero vehicles, then the equation will be simplified to this. Zero vehicles means your headway is more than the time for which you are looking at the number of vehicles or arrival of the vehicles. Okay. Then we talked about complementary probability, and if you add them, you will get 1. Okay. So we have 360 vehicles per hour. Okay. So this becomes my lambda. Okay. 360 vehicles in 1 hour. Okay, this becomes my lambda. So let me. Okay, total vehicles 360 in how much time? Capital T, 1 hour. Okay, assuming the arrival is Poisson distribution, estimate the probabilities of having 0, 1, 2, 3, and 5 or more vehicles. Okay, so for zero vehicles. Now this is my lambda. Okay, in over 20 seconds. Okay, 20 seconds. So my small t is 20 seconds. Now, since the lambda is in hour, so I need to convert this into hour as well. So 20 seconds means how many hours? Like how much in hours? 20 divided by 3600. Or we can convert the 360 into per second as well. Uh, so hours multiplied by something. Okay, so 360, uh, let us do it with 360. 360 divided by 360 per hour divided by, sorry, converted to per second. How much? 3600 seconds. So how much is this? Huh? No, no, you will divide. Hours in the denominator, right? You will divide. 360 per hour, right? You're converting per hour. Okay, so it's per hour. Okay. So I don't need to do this. I can just simply write here 0.1 vehicle per second, right? I converted the lambda. Okay. Now probability of zero vehicles. We already simplified the equation, so I will use this one. So exponential to the power minus lambda into t. Okay. Exponential minus lambda 0.1. So t will be 20. So how much is this? How much is this? 0.135. Okay. So which is over here. Okay. Similarly, I will show you for one vehicle. Now, for one vehicle, I cannot use this. Okay, this is a simplified equation for zero vehicles only. For one vehicle, I go back to the basic equation. Okay, the first one, which was simplified. Okay, so I need the so this is the big bracket. Okay, I need lambda into t. So 0.1 into 20, then exponential to the power minus this over x factorial. X is 1. So 1 factorial. Okay, how much is this? Okay, so you can see 0.27 is here. Okay, similarly for 2, I replace 1 factorial with I think I missed something here. No, yeah, it was to the power x. So this thing to the power 1. Okay, so for obviously now it will not make any difference, but for probability of 2, this will be replaced by 2. So here it will be 2 and the factorial will be 2 as well. Okay, for 3 it will be the x will be changed to 3. So here factorial will be 3 and this one will be 3 as well. Okay, so on and so forth. Okay, so you can calculate it yourself. You can check the probabilities over here. Okay, for 2, 3, 4, and 5. Sorry, yeah, for 2, 3, and 4. Now I'm interested in this one, 5 plus. How do I calculate this one, 5 and above? How do we calculate this thing? 0.053. Because all this equation gives me a probability of one number. Okay. Now 5 plus it can go up to infinity. Okay. When I say 5 or more vehicles, so I'm not talking about only about 5 or 6 or 7 or 5, 6, and 7. Okay, I'm talking about 5 up to infinity. 5 up to infinity. So how can I calculate this value? These values for single x values. So they are easy. Okay. But what should I do with this one, which has multiple values?
1
Eh,
minus the previous
Yes,
probabilities.
yes. Okay. The rule of complementary probability. If the probability of not having 5 and more is this thing, okay. So when you are not having 5 or more, you can either have 0 or 1 or 2 or 3 or 4. Okay. Anything which is not in these 4 or in these values will be 5 or more. Okay. So probability uh, so equal more than 5. Okay, so either it is equal to 5 or more than 5. Okay, so I'll take 1 minus probability of 0.135, probability of 1, probability of 2, probability of 3, probability of 4. Okay, so this should give you 0.053. Okay, so whenever you are looking at multiple properties, you can use this property. You can use this property, the complementary property. Okay, so any value which is not from 0 to 4 is 5 and above. So you 1 minus all the properties from 0 to 4, you get the probability of 5 and above. Okay. As I said, you can calculate the probability of 2, 3, and 4 yourself to just check if you're getting the right answers or not. Okay. Any questions?
No.
Okay. Moving on. We have same situation now or same flow, 360 per hour. And we are again assuming that the vehicle is Poisson distributed. So the equations for Poisson distribution, okay, if, distribution will change, you cannot use the same equation. But normally in traffic engineering literature, you will find they assume it is Poisson. They already did some studies and they found that Poisson is the best thing to be fitted here. Okay. What is the probability the headway between two successive vehicles will be less than 8 seconds? And what is the probability the headway between two successive vehicles will be between 8 and 10 seconds? Okay, so uh, I'll basically what we are doing here is using this one. Okay, so we are looking at which one headway is less than 8 seconds. So headway less than t, remember, headway less than t, this one. Okay, where t is 8 seconds and headway less than 8 seconds. Okay, so I'll be using this equation. Okay, so lambda is still same 360. So 360 converted to per second is 0.1. Okay, and t is 8 seconds. Okay, so what we are doing here is 1 minus exponential minus zero point 0.1 into 8. How much do we get? 0.55. Okay. So P where headway is less than 8 seconds. 1 minus, okay, 10.5. So there's 55% probability that the headway will be less than 8 seconds. Okay. Now they are asking for the headway is between 8 and 10. Okay. So I'm looking for between 8 and 10 means that first of all, I'll calculate the probability of headway to be 10 or more. Okay, and then I will subtract it from this one. Okay, so headway to be 10 or more. So I'm using this one. I already have for 8 and less. Okay, now I calculate the probability for 10 and more. Okay, so uh, I'll do this one. Okay, but my t will be uh, 10 seconds. Okay, so uh, probability headway is 10 or more. So how much is that? 1K68. Okay, so between probability headway, now you need to see what you have done. Okay, so I have done for uh, less than 8. Okay, so my headway can be equal to or more than 8. Okay, and it is I did it here for equal to or more than 10. So my headway will be, that means it will be less than 10. I did something here. Yeah, so headway will be more than or equal to 8, but less than 10. So this is what I've done. Okay, you need to be careful. So I have only done for less than 8. So there is no equal to sign here. Okay, so I have to put equal to with this one. Okay, so headway is more than or equal to 8, and there's equal to sign here. So equal to 10 is not included here. Okay, I'm looking for headway less than 10, not equal to. Equal to already is here. So when I take the difference, equal to is already gone. Okay, so 0.55 minus 0.368. How much? Okay, so there is like 18% chance that the headway will be between these two values. There's 55% chance the headway is less than 8, and almost 37% chance that the headway is uh, greater than or equal to 10. Okay, the point was that you need to, this is between 8 and 10, but you need to be careful where to put the equal to sign. Okay, so equal to sign is not, so the probability I'm subtracting for 8 does not have a equal to sign. So after subtracting, the equal to will be included. Okay, so basically whatever you have here, okay, will be the opposite here. Okay, when you will subtract. So any questions? Okay, moving on. We have now this one. Let me zoom it in. Okay, so the data is given here for 1 minute intervals. Okay, and we recorded it for 15 minutes. Okay, total 15 minutes. So now for these 15 minutes, I have the data. So now they are looking for the next intervals. What will happen after 12:15? So using this data, we will predict or simulate what will happen after 12:15. Okay. So what are they asking for? Calculate what is the probability that 6 or more vehicles will arrive in each of the next 3 intervals. Okay. So after 12:15, in each of the next 3 intervals, what is the probability of having 6 vehicles in all of them? Okay, all of them. So I'm basically there is no we're not talking about headway. Uh, we are talking about the what you call the 6 or more vehicles. Okay, 6 or more vehicles. So what is the probability that we have 6 or more vehicles in the next 3 minutes? Okay, each one of them. Okay, each one of them. If you consider each minute separately, then the probability will be calculated using this equation. Okay, so you will have probability of 0 to 5 vehicles, and you will do 1 minus that, it will be 6 or more, like we did in this question. Okay, so they are asking for 6 or more vehicles in 1 minute. Okay, so for any minute, probability of having 6 or more vehicles will be 1 minus probability of having 0 to 5 vehicles. Okay, so that is that. So it's written over here. You can see this one. Okay, probability of having 6 or more vehicles means 1 minus probability of having 0 to 5 vehicles. Okay, so you calculate the probability for each one, 0, 1, 2, 3, 4, 5, and you will add it here. Okay, so this will give you probability of having 6 or more vehicles in any minute. In any minute, it can be this one, it can be this one, it can be this one, any minute. Okay, so let us begin with this one. Okay, so first of all, to use this equation, I need lambda. Okay, and I need small t. Now small t is 1 minute. Okay, now you can keep it as 1 minute. Okay, you can keep it as 60 seconds. The difference will can be lambda. Okay, so lambda is for 15 minutes. So what is my number of vehicles in 15 minutes? Tell me. How many vehicles are these in 15 minutes? Yes, what is the summation of vehicles in 15 minutes?
101.
101?
Yes.
Okay, so that means my lambda 101 vehicles per 15 minutes. Okay. So how much per minute?
6.7.
6.7. Okay, so I will keep it minute. Okay, per minute. I'll keep it as minute because the time is also in minutes. So no problem here. Now, I need one to do 1 minus the summation of all the probabilities. Okay. So I'll be using this equation. Okay, the last one. 6 times. 1 for 0, then for 1, then for 2, then for 3, then for 4, then for 5. Okay. So each time we'll be doing this. I'm looking for this thing. Lambda is 6.7. I need to take the power. So the first time it will be 0. This is 1 minute. 6.7 into 1. So 0 factorial minus. Then everything will be same for 1 factorial. Then 2. Then 3. Then 4. Then 5. Okay. So probability of having 0 vehicles, 1 vehicle, 2 vehicles, 3 vehicles, 4 vehicles, 5 vehicles. And 1 minus all of them is 6 or more. Okay. So how much is that? Yes. How much is this? Point 0.65. Sure. Okay. Thank you. So this thing is 0.65 then. Okay. This whole thing becomes your point. So there's 65% probability that I will have 6 or more vehicles in any given minute. Any given minute. Okay. And as I said, it could be from 12 to 1 the first minute or the 15th minute or the 16th minute, any minute. Okay. But in the question, they are not asking for any minute. They are saying the next 3 intervals, all of them have 6 vehicles. Okay. So this is what we call as the conditional probability. Okay. The conditional probability. So what is a conditional probability? Probability of having or probability of something when something has already happened before it. So we are saying probability of having 6 or more vehicles in the third minute when I already have 6 or more vehicles in the second minute and 6 or more vehicles in the first minute as well. Okay. So I can only fulfill the condition of the equation of the question when each of the next 3 time intervals have 6 or more vehicles. Okay. So if only 1217 to 1218 has 6 or more vehicles, then I do not fulfill this condition. To fulfill this condition, all 3 of them should have 6 or more vehicles. Okay. So this is the case of conditional probability where you are saying, yes, this should happen, but before this, this should have also happened. Okay. So whenever we are talking about conditional probabilities, then you multiply the probabilities of all conditions. Then you multiply the probabilities of all conditions. Fortunately, in the case of this question, I'm looking at the same condition 3 times. 6 or more vehicles 3 times. Okay. So I just multiply 0.65 by 3. Okay. I multiply 0.65 by 3. But whatever, okay, but whatever the conditions are, you will multiply them to get the conditional probability. Okay. So if I'm looking for 2 vehicles in the first minute and 3 vehicles in the second minute, so I'll calculate the probability of 2 minutes and calculate the probability of 3 minutes and multiply them. Okay. In this case, 6 or more vehicles 3 times. Okay. So probability of 6 or more vehicles multiply 3 times. Okay. So 0.65 into 3, how much? Yes. How much is the probability of 0.6? This 3 times? Huh? Oh, okay. There is something. No, no. Sorry. Not like this. Like 0.65 into 3. Sorry for that. You're multiplying the probability, not the number of times. So 0.65 into 3. How much? Oh, sorry. 0.65 into 0.65, 0.65. The power of 3. Sorry, not multiply by 3. Power of 3. You're multiplying the probabilities. Okay. So 0.65 into 0.65 into 0.65. How much? 0.274. Yes. Okay. So probability of having 6 or more vehicles in one interval is 65%. Probability of having them 3 times consecutive is 27%. Is what we are saying here. Okay. Clear? Any questions?
Clear.
Okay. Moving on. Now we come to how we can use the equation. Now remember we had an equation here for headway. Okay, headway is t or more than equal or more than t. Okay, this was the equation. Now headway is the gap between the two, right? The gap between the two vehicles. So for example, if I draw 3 lines here, line 1, line 2, line 3. Okay, so I have 3 lines. If I have 3 lines, the number of gaps is 2. See, between line 1 and 2, gap 1. Between 2 and 3, gap 2. So if I have 3 lines, I will have 2 gaps. If I make another one, so I have 4 lines and 3 gaps. Okay. If I make another one, 5 lines and 4 gaps. Okay. So the number of gaps are always one less than the number of lines you have. Same thing goes with the vehicles. If I have a V number of vehicles, then the gaps between them will be V minus 1. Okay, the gaps between them will be V minus 1. So let's say one gap equals to H. Okay, so and H has a probability of this exponential. We are getting it from here. Okay, so the probability of okay, I lost the connection for a while. The probability, so I was saying probability of having a H gap is this much. Okay, so how many gaps I can have for this H? I will I will multiply with the number of vehicles minus 1. So V is the number of vehicles. Minus 1 will give the number of times you will have the gap. Okay. So if the gap is, I'm looking at the gap equal to T, then the probability of having, the number of gaps or number of times to have this gap will be V minus 1 into the probability. Okay. So this exponential gives the probability of having gap or the headway equal to T. And V minus 1 will give you how many times you can have it. Okay. So without V minus 1, if I remove the V minus 1 from here, I have the probability for having one gap. Same thing here, but what we do here. See, remember? So it's a conditional probability, right? It's a conditional probability. Okay. So the gap between two vehicles equal to H is this much. Okay. Then what is the probability? That the same gap will be between all vehicles. So I'll multiply with I will multiply the probability with the number of times I'm having the gap. Okay. So the number of gaps I can have is V minus 1. Number of vehicles, if I have 2 vehicles, I have one gap between them. So 2 minus 1. If I have 3 vehicles, I have 2 gaps between them. So 2 minus 1. Oh, sorry, 3 minus 1. Okay, and so on and so forth. So this gives you uh, how many times in a traffic stream you can have a gap of uh, t or less. Okay, in a traffic stream, how many times you can expect the gap between the vehicles to be t or less. Okay, and if you want the other probability, how many times I can have a gap of t more than t, then you will do the complementary. So instead of multiplying by exponential, you will multiply by 1 minus exponential. Okay, so this is probability of having one gap. Multiply with the number of gaps you have the probability of having number of gaps of this size in the traffic string. And if you want the probability for less than this value, then you go to the complementary probability. So instead of multiplying with exponential, multiply by 1 minus exponential. Is it clear? Any questions? Okay, let us look at some examples, make it clear, inshallah. So we have in 1 hour 1800 vehicles, and the arrival is Poisson distribution. As I said, these equations are for Poisson distribution. We are looking for a critical gap of 3.5 seconds. Okay, so we are looking for the expected number of acceptable gaps. Okay, now for ramp vehicles that will occur on the expressway during the peak hour. So they are saying how many times my gap will be more than 3.5 seconds. Okay. Anybody remembers what we mean by critical gap? I explained it last time. What is the meaning of critical gap?
There's a 50-50 chance for
Yes.
the driver to enter or not.
Yes. Okay. So acceptable gap is that gap which is more than the critical, basically. Okay. Acceptable gap. So the chance of driver entering will increase, right? When your value is more than this much, then the chance will increase. Okay. So I'm looking that the headway will be more than 3.5 seconds, equal or more than 3.5 seconds. So I'm looking at this value. Okay. And my V is 1800, but this is 1800 per hour. And your lambda and t will be in seconds. So you need to be careful here. Okay. So first of all, I'll convert my V to seconds. So this is how much? How much is that? Yeah. Okay. So my V is 0.5 because I want it in per second. Okay. Because my time is in second. So now probability that headway is equal or more than 3.5. Okay. So uh, um, okay. Okay. I shouldn't do this. I don't need to do this because this is from another equation. Okay, we are just simply multiplying with the number, right? So we don't need to do this. There's no time here. Okay, we will just take 1800. Okay, sorry for that. We don't need to do the conversion. We just need the number. We are doing it for 1 hour, right? How many times this gap will occur in 1 hour? So we don't need to do it. Okay, so the exponential. Okay. So for V, I don't need to do it, but I need the lambda. Okay. So yes, I do it for lambda. Okay. So lambda, you need the conversion because lambda is in the same equation. 1800 is just a number because I'm looking for how many times it will occur in 1 hour. Okay, so there's no problem. So this is for the number. For the number, we can keep it same. But for lambda, we need to change it because it will be multiplied by time t. So if you see here, so lambda into t. So you cannot multiply lambda, which is per hour, into t, which is in seconds. So that's why I'm doing it. Okay, so for lambda, I need to do it. 0.5 to 3.5. How much is that? 312.
312.6.
312.6. Okay. Okay, so not the, but the number. Okay. So almost 312 cars can pass in 1 hour. And 312 cars will find the acceptable gap in 1 hour. This is what it means. Okay. So there's a expressway and there's a ramp coming on the expressway. On the expressway, the flow is 1800 vehicles per hour. Okay. The people which are coming from the ramp, they are more likely to enter from the ramp if the gap is 3.5 seconds or more. So this is the probability of having 3.5 seconds or more. And how many times it can happen? 1800 minus 1. Okay, number of cars or number of vehicles minus 1. Okay, so they will find the acceptable gap almost 312 times. Okay, so in this flow, 312 cars or 312 vehicles can enter from the ramp with this much flow. Okay, and similarly, you can do it for other values as well. So you can take it as a practice and you can do it. Okay, how many times they will find a gap of 0? How many times they will find a gap of 1 and 2 and 3 and so on and so forth. Okay, now looking at this table, okay, uh, theoretically, I can put t equal to 0 here as well. It will still give me an answer. You can see there's an answer here. Okay, there's a probability here, there's an answer here. Yeah. But is it reasonable to say that somebody will enter the traffic stream with 0 gap? Is it possible? You have 0 gap and you can enter. Is it possible? Yes or no?
No.
No, yet. So 0, like we should not start the calculation from 0. Okay. Similarly, 0.5. It's a very, very small gap. 0.5 is less than a second. Can you enter when there's no gap, like less than a second of gap? No. Same thing with even 1 second. Okay, 1 second is a very dangerous gap to enter. You are not giving a time to driver to react. Okay, so there's always a minimum value of gap as well, where any driver will dare to enter. Okay, but that only comes from the drivers. Mathematically, I cannot find. Okay, so there's an acceptable gap where the driver has more chances of entering, and there is a minimum gap where drivers will practically not even consider entering. The equation will not tell you this. Okay. So what we do is we introduced a term tau here. Okay. And tau means the minimum gap at which drivers start to think that they can enter. So let's say that minimum gap is 1 second. So tau is 1 second. Okay. If I go back to the previous example, okay, and repeat it with a gap of with a minimum gap of 1 second. Okay, so what was I doing? Number when h is 3.5 with minimum 1 second. So it was 1800 minus 1 exponential by 0.5. Okay, uh, into 3.5 minus tau 1. Okay, so how much is this?
515.
Huh?
515.
515. Okay. Okay. So you can see now the probability has, or the number has increased. Okay. So now with the adjustment for minimum head weight, where nobody will consider it pointer. So what is happening? The See this number. Okay. So there was a number when probability is when the gap is 0.5. There was a number when the gap was 1 second. So this number has shifted now to this value. Okay. So basically anything less than 1 is 0 here. Okay. Anything which is less than 1 is 0 here. Okay. So because no cars will try to enter when the gap is less than 1. Okay. So that extra probability has shifted to the other values. Okay. So basically when you are the point is, or the trend is, when you introduce the minimum gap, okay, the chances of acceptable gap will increase. Okay, because the chances of having less than the minimum have become 0. Okay, so the summation of probability has to be 1. So those chances which are less than minimum will be now distributed among the real values, the values which are more than minimum. Okay, so this is why you see a higher number here, 515. Okay, so uh, the point is when you introduce a minimum gap, uh, you will find the number of available gaps will increase. Okay, because the probability less than minimum distributed in the available values. Okay, that's why. Okay, the next item is queuing theory. Uh, that I will start next time, inshallah. So, are there any questions?
No, thank you.
Okay, I believe we have everybody here. Habra was here or not? She was not here. Okay, fine. So thank you. I'll be taking the attendance. Only Habra is not here. And see you next time, inshallah.